Right. So you guys can hear me, right?
Yeah.
Yep.
Yes, sir.
Thank you. So let me grab a pen. Hope this should work. Okay, so today I'll let me start with some nice picture. I'm not good at drawing, so let me show you the picture here. Can you guys see the slide?
No.
I see your library.
Yeah.
Okay, let's see. Screen share.
Oh, Jesus.
How about now?
Yeah.
Okay. Can you
What's
see?
the problem, Anthony?
My dog just farted on me.
Huh?
Sick. Small poop clouds, no big deal.
Do you see the slide now?
Yep, linear and angular velocity.
Okay, very good. So let me begin with this one here. So angular velocity. So I don't have to talk too much about it because you know this. This is a kind of a physics one, right? Physics one stuff.
Mm-hmm.
So right here, what I'm trying to recall here is you have the rigid body. Let me use my mouse here. You have the rigid body. You can see this is the rigid body, right? This guy, this is the rigid body, and this rigid body is rotating about this axis here. Okay, and we assume for now the axis is fixed. So meaning this coordinate system is not moving. Okay, this coordinate system is not moving. Only this guy is rotating, meaning this is just the pure rotation. There is no any kinds of translation. Okay, just pure rotation. So what happens in this case? All points of the rigid body sweep out a circle. So take any point, you name it, then when the body rotates, then that point rotate in a circle as shown in the figure. Do you see that? Okay, this, suppose if you take a point here, it rotates in a circle. If you take another point somewhere here, maybe, where is my mouse? Here, that point is rotating in a circle. If we take another point here, rotate in a circle. So there are, millions of circles there, right? So one thing we can conclude about all those circles is that that axis is perpendicular to all those in a circle. The circle is a 2D picture, 2D figure, right?
Yeah.
So perpendicular to that 2D figure, which is circle, there is an axis which is fixed and about which the entire rigid body is rotating. So there is no any translation motion. Okay. So what is the direction of omega here? So in this, so let's say this is I don't know, if you say this is k direction, then it's in the direction of k. That's the omega, right? Okay. In other words, So omega equals theta dot k. Because if you do not take, if you do not consider the direction of omega, then that's theta dot, right? But if you consider, let me stop it here and well, I had this good, better picture here. Let me continue here. Okay, so does this make sense? Omega equals theta dot. Theta dot is d theta by dt, right? So change in angular displacement with respect to time, or rate of change of angular displacement, is the angular velocity. Okay, and if you want to show the direction, then the direction is k. Okay, this direction is, so this is k direction. That's what I meant. Okay, this direction is k.
As in like the Z.
Yeah,
Yeah.
yeah. So now this is, we talked about angular velocity, right? So now let's talk about linear velocity. Because even though this is moving in a circle, right? As we saw in the previous slide, this P moves in a circle, right? But even though it has just motion in circular path, so this guy also has linear velocity, because it's like if you consider something moving in a circle, and if you somehow release something at some point in the circle, then it will just go tangentially, right? So that's why there is also associated linear velocity. Okay, so this at point P there is linear velocity. And what is the linear velocity then? So since this is the angular velocity, and this is r, from here to here is the distance, the vector r.
Yeah.
So then what is the linear velocity? The linear velocity will go tangentially, right? This way rather, in my picture. It go tangentially. So it means, how do you get V? That B equals omega cross r. So if you see the right hand rule, okay, omega cross r. So that gives you the velocity of the point P here. Okay, linear velocity, this is how the linear and angular velocities are related. So B is the linear velocity, omega is the angular velocity, and r is the radius vector here. Okay, this is r. This is the relationship between V and omega. So this is just from physics 111, okay? And here we assume that origin is on omega, meaning on this axis. On this axis, there lies the origin, okay, right here. Okay, this is the assumption. So this is just a recall from physics 101, 111. Okay, now, question?
No.
Okay. Now, yesterday we proved this, right? So yesterday in the previous lecture, we proved this expression here. We proved this one, right? R dot equals lambda times R. That's what we did day before, right here. Okay. So a couple of slides back. This is the last slide of the last lecture. Okay. So we spend some time to derive this equation. So R dot equals lambda times R. So that's what I have here. Okay. R dot equals lambda times R. Now, based on the knowledge so far we have, I'm going to prove that, see this lambda. So what is the lambda here? What did we say here? Lambda is time varying symmetric matrix, right? So that's the lambda. Now I know this is symmetric matrix, but the thing is, what I'm going to prove here is, now this is not only symmetric matrix, this is symmetric matrix which has the vector component, of angular velocity. So this is vector. Obviously, this the symmetric matrix can be represented by a vector, right? So that vector happens to be omega. That's what I am going to prove here. So this is skew symmetric matrix, and skew symmetric matrix is related to a vector, and in our case, that vector happens to be angular velocity vector. That's what I'm going to claim here. Okay. All right. Let's begin with my definition of p dot 0 equal. So let me write this down here. Okay. Let me do the other one. Stop sharing and let me do it here. Okay, that's my goal, right? So let's prove that. So lambda equals S omega t. That's what I'm trying to prove. So we know R dot equals lambda R, right? That's what we know from last lecture. Okay, so are you guys aware of this relation here? R1, 0, P1. Do you remember this relation?
What's P1?
P0. This is P0, yeah, and this is P1.
What does the P stand for?
No, P is the radius.
Okay.
So this is from chapter 2. Remember we did a lot of this kind of stuff?
Yeah.
Yeah, I can show you some of the picture that will recall your memory from previous chapter, okay? So in the next slide, I will have that. So for now, so since we did this a lot in the previous chapters, just I will take it from there. Okay, so if you take the derivative of this guy, what is the derivative of this guy? So d over dt r1 0 p1, that's the derivative. Now, so first function as is, the derivative of second function plus derivative of first function, then second function, right? That's the chain rule.
Yeah.
So this guy p dot 0, let me show you in the, before I move on, let me show you the picture. I don't want to make, confuse you guys here, right here. Hold it, my slide. So do you see my slide now?
No. We're at the library.
Not the slide?
Nope. There we go. Oh, never mind.
Let's do it again. Hopefully you'll see it now. How about now?
It's showing the folder. The folder where you have the slide.
Oh, just the folder? How about now?
Yep.
Yep.
You see the slide now?
Yep.
Okay, very good. Now what I meant is this, let me, hopefully this will, yes, see that? This is what I meant. I think that refreshes your memory now, right? So this is what we did in the chapter 2. Okay, so I'm taking this exactly the same equation here, this equation. P0 equals R10 P1. Okay. Now, what is this P1? P1 is, what is P1? Look at this picture here. P1 is the distance of this point related to, with respect to this blue coordinate system, right? This blue, which is rotated frame, right? Okay, the point P is on the object. The object is rotating. Because object is rotating, and in the same time, this frame is also rotating. So what do you think? What is the rate of change of this P1 in this picture?
Say again.
What is the rate of change of P1? P1 is this distance. P1 is the distance from here to here related to this frame, this blue one. See the blue frame?
Yeah.
Blue frame is the rigid body which is rotating, and P is the point on the rigid body, this point P, and the distance with respect to rotating frame is P1. Then what is the rate of change of distance? 0, right? Because with respect to rotated frame, the distance does not change because that point is fixed. That point is on the rotated object, rotating object, meaning rate of change of P1 is 0. Does it make sense?
So how that equation, that circle with the red circles, that's how you get the rigid body from Y1 to P1?
No, don't worry about this. I'm trying to just show you this picture, not anything
Right.
else. Okay, not anything else. Okay. So this is the fixed axis, x0, y0, and this blue one is a rotating axis.
Yep.
And that rotating axis is on the rigid body. So of which this point, this P is a point of that rotating body. So in that case, what is the rate of change of distance of this point P with respect to rigid this rotating object? There
Like from the origin of the reference, or
from here.
that be just the line, the green line, the red line from?
No, just the origin here. This origin right here. This origin, because with respect to this origin, so this point is not moving at all, right?
No.
Yeah, that's why I meant. So with respect to this origin, the blue one right there, with respect to this origin, this point P is not moving at all.
Okay. Yeah. All right. I
Okay.
thought. Okay. Yeah. I got that.
Okay, that's why P1 dot is 0. That's what I'm trying to say.
It's just reference frames.
Yeah, it's the reference frame. So that's why P1 is 0. Okay, so are you still seeing the
We see the clipboard.
Oh, okay, that's nice. All right. So okay, now how about now? That's why this P1 dot is 0.
Okay.
So that's why your P0 dot equals R10 dot P1.
Which is just lambda R.
Exactly. This guy is lambda R. Okay.
And then do we plug in lambda after the S omega T?
Oh, don't worry about it. So this one, I'm using this relation here.
Yep.
Okay. So lambda. So this guy R10 dot is lambda R10.
Right.
Using this expression.
Yep.
So far, so good.
Yep.
Okay. This is one of my equation. Now let's use another equation here, which you are very familiar with. So B equals omega times R, right?
Mm-hmm.
So in our case, we are calling it P. Instead of R, we call it P. Okay. So if you want to use our exact notation, this happens to be P dot 0 equals omega P0. That's what I meant. In our notation, this guy is exactly this. They are exactly the same. This is our notation. This is our previous understanding, right? This is how you used to write. Now,
Yep.
this is how we rewrite this guy now. This is now. So what is a P0 from here? From here.
0.
So can you write this guy as this? Omega cross R10 P1.
You're writing out the screen. There you go.
Does it
Yep.
make sense? So
Yep.
this is now equation 2. Now they are exactly same. See, this one is P0 dot. This one is P0 dot.
Yep.
So 1 and 2 are same. So can you equate these two? Now
Yes.
equate these two. Lambda R10 P1 equals omega times R10 P1.
And P1's.
They're equal.
Is this all Jacobian?
No, not yet. Now from here, what do you see?
P1's cancel.
I mean, there's a R01 and P1 on both sides, but the right side has a cross.
Yeah. So
P1 can be pulled out.
do you huh?
Yeah, wait. I think I know what Anthony's saying. If we said that P1 is equal to 0 earlier, can we do it again?
Or where? Here?
Wait, probably not, because then it's just as W equals 0.
No, this is 1, and here we have dot. Remember, this is
Oh,
dot.
dot. Yep. Okay.
Dot is 0, not the non-dot one. Okay.
Yep.
So now I wanna use one property here. So remember, we had a property, this property, as A P equals A cross P.
Yeah.
Okay. So can you write this guy on the right hand side? This guy as, how do you write in that by using that?
It would be W, well, omega.
So yes, omega.
Yeah, RP.
R10 P1.
Yeah.
That's your right hand side.
That
So,
looks a lot like the top.
and R10 P1. That's your left hand side. Left hand side is as is. So
One thing.
yeah, go ahead.
Do we have to do something with the top equation with the lambda?
So this one,
Left. The middle of the page, top of the, yeah, that.
no, this is our goal.
Oh, that's what we're trying to get?
Yeah.
Yeah. Then the R.
Oh, we're close then.
Okay, now,
Did you just divide the R0, divide both sides? Yeah.
so you got the idea. So this guy cancel. Now your lambda is S omega.
That was cool.
Yep. So that's how we prove this.
And you said this is not Jacobian?
Not at.
Okay.
So
Oh, well, there's more.
Pardon me, Professor. Before you switch the page,
yes.
oh yeah, just gonna take a photo of it.
No, I'll upload the video. Remember? Don't worry about it.
Oh, okay, thank you.
Yeah, I'll upload all the videos, so don't worry about it. Okay, now this is so cool. So now this guy, how do you write this guy now? R dot equals S omega R. Did you see that? So now my rotation matrix, the derivative of rotation matrix has the omega component in it. We are trying to get the omega component in the rotation matrix already.
Oh, okay.
Right? Now let's do one problem, one example, then I'll move on to the next thing. Now let's do one problem here. Let me show you the problem, then let's see. Do you see my slides?
Yep.
Okay, very good. Let's do one problem here, this one. So let's do one problem. Compute dr, d over rate of change of rotation matrix. What is my mouse? So what is this guy? This r x theta means rotation about x-axis by angle theta.
Yep.
What is the rate of change of that matrix? So we need to figure that out, okay? So I think you guys will understand. I don't think I have to write this down on the page. So I think it's straightforward. So we already know this r dot equals lambda r. Does it make sense? This guy? Okay. So this guy makes sense. Now by definition, lambda is this. This is the definition of lambda, right? Now let's do the derivative of this guy here. What is this r?
It's the X rotation matrix.
Rotation matrix, right? You remember that, right?
Yep.
Remember, so you have all 0 on the first one. Your x is 0. Then you have, you know, sine and cosine term.
Yep.
So now you have to take the derivative of everything. So derivative of 0 is 0. Derivative of 0 is 0. This is 0. Derivative of this is 0. And you had the cosine term here.
Yep.
So what is the derivative of cosine?
Negative sign.
Negative sign. Then
No.
that's the chain rule, right? With
Yep.
theta is negative sign. With respect to time, because you have time here, that's why, which is theta dot.
Yes.
Okay, theta dot is here. Similarly, here you get negative cosine theta theta dot. Here you get cosine theta theta dot, and negative sine theta theta dot. That's what you get. Now, what is your RT? Transpose of rotation matrix. Okay, this is the transpose of rotation matrix. This whole matrix is transpose of rotation matrix, right? Okay. Now what you need to do is now you multiply this together. If you multiply this matrix together, what do you get? So I'm not going to do the multiplication here. So you know how to do matrix multiplication, right? If you multiply this guy with this guy, what do you get? 0 times 1, 0, 0 times 0, 0, 0 times 0, 0. So that's why your first term is, first component is 0. Similarly, you repeat the same process, then you get like this. So by the way, you get here negative theta dot, you get here theta dot when you do that. So in that case, I can take theta dot out, right? So if I distribute all the elements, if I distribute theta dot to all the elements, then I happen to get negative theta dot here and theta dot here. That's why I simply take out theta dot here. So what is this matrix, by the way? This matrix here. What is this matrix? Is this SI?
Sure.
Let me show you here. We did that before. Remember right here,
Oh yeah.
right? This is your SI.
Mm-hmm.
0, 0, 0, 0, 0, negative 1, 0, 1, 0. So that's what we have. So that's why you got SI there, okay? So this is SI, then theta dot. So where I is obviously 1, 0, 0. Okay? So if you happen to take the derivative with respect to theta, what happens? Just a, you know, tail question here. If you happen to take the derivative with respect to theta here, this t is now theta.
You would get rid of the theta dot terms.
Exactly. Okay, that's why. So if you do the derivative with respect to theta, then you get rid of this theta dot term here, right here, this guy. You simply get SI. Okay. So we figure out our lambda. So once we figure out lambda, you just plug in the R there. That's it. So main problem is the lambda, right? Once you figure out lambda, then you simply plug in R, then you get this relation here. Okay, this is my lambda. Yes, I is lambda.
Okay.
Makes sense?
That so that is how we can, like, that's just answering the top dot.
Yes, compute this guy in terms of Rx theta, right? That's how you answer the question. Now, similarly, I could ask you, okay, compute d over dt, a rate of change of Ry theta instead.
Right.
So then Rg theta, okay, in the same way. So you guys can do this in the same way, right? So very good. Now this is my conclusion. Now this is conclusion. So once I have this, then I'll go to the next slide. Now this is what we did so far. R dot equals skew symmetric matrix of vector omega or angular velocity. Then multiply by RT. That's your R dot. So in other words, this is the skew symmetric matrix which has the components. Remember, the skew symmetric matrix has 3 components, X, Y, Z. Okay, those X, Y, Z components are the components of angular velocity. Okay, so in the rotation we are getting the angular component here. Okay, now I wanna a little bit warn you guys about notation change, because it depends on the book now, you know, in the book, and also here we want to accommodate something. That's why we want to change the notation here. So remember, how do you represent the rotation matrix? Rotation matrix is represented by this thing, right? Which is RJI, meaning rotation of J with respect to I. Now, in the same way, if you want to write the corresponding omega, how could you write? You could write omega J, then I here, right? That will be the corresponding omega. But we don't write that way because there is a reason. Instead, we write this way. We could have written this way, but for some reason, I'm going to write this guy as this. So because I'm writing this way, because so I'll have some instances that okay, let me say it this way. So I'm writing this here this way because I will have one more index here like this. Do you see that? I'll have one more index. Instead of 2, I have I and j. You can call k now. This is k. Let's say this k. This 0 is k now. I have 3 indices. So I will have 3 indices in the upcoming topic. Okay. So what does that mean is, obviously you understand this, right? 0 and 1, because this is exactly this way. This is exactly this, meaning angular velocity of j frame with respect to I frame. Okay. And what does this k represent then? The superscript. So that represents expressed in k frame. In other words, if I have omega 0, 1, 0, it means angular velocity of frame 1 with respect to 0 frame written with respect to 0 frame. Okay, this k is this 0 here. Does it make sense, guys? So angular velocity of frame 1 relative to 0, okay? Frame 1 relative to 0, written relative to frame 0, okay? So we need that kind of notation. That's why we are writing this omega ij as such.
Okay.
Okay.
Yep.
So, but there is a, I want to warn you guys, there are some books that, you know, if there are angular velocity related to base frame, then they generally drop the superscript, meaning they don't seem, if it is related to base frame, right? Okay. If it is 0, this I is 0, base means 0 frame, then they simply drop the 0 on the top, superscript.
Okay.
In some books you might find that, but you know, I would like to follow the convention. Okay.
Yeah.
I don't want to drop it, you know, that gives you more confusion. But the thing is, if you get some other books and if you see like that, don't get confused. That's what I'm saying.
Okay.
Okay. Now, now I'm talking about the adding angular velocity. Now we want to add the angular velocity. So suppose what happens is in our robot, because we have different links, right? Link 1, link 2, link 3, you know, there could be n numbers of link. Then you have to add the angular velocity of the first link to the second link and third link and stuff like that. So it means you have to able to add all those angular velocity eventually. That's how you get the resultant effect at the end. Okay. So in that case, how do you add the angular velocity? Okay, that's what we're going to talk about now. So for simplicity, let's begin with two-link robot. Okay, for the two-link robot, so what is the rotation matrix for the two-link robot? So you have two links. That's why you have, you know, frame 0, 1, and 2, right?
Yeah.
So how do you write the rotation matrix for the two-link robot? Just like chain rule, right? See that 1 and 1 cancel.
Yes.
R1 0, R2 1. Now if you take the derivative of this guy, what do you get? Take the derivative. So this is dot, on the left it is dot. Then on the right you use the chain rule, right?
Yeah.
So R dot 1 0, R2 1. That's the first one. Then R0 1. Then take the derivative of second one.
Yep.
Okay. Now remember, we have this expression here. We proved that, right? So we'll be using this guy. R dot equals S times R, right?
Yes.
R dot equals S times R. So
Yep.
that's what we'll be using now. Okay. So this is exactly from the previous slide. This first line is exactly same thing from previous slide. Now let's use that. Let's use this guy here, which already know, we already know this guy, right? So let's use that here. Now, wherever you see R dot, you just plug in this. So you don't have to worry about this guy, R21. You have R21 here. Don't worry about it. This is R21. Then R10 dot. What is this guy? From here.
Yeah.
R10 dot is, help me here. Yes, 0 1 0. Sorry, S omega 0 1 0.
Yeah.
Times what is the other one? R10.
Yep.
That's what your R dot 1. Then similarly, this does not change. This is exactly same as is. Then R dot 2 1. Again, use the same guy.
Right.
Then you get this again. Okay. So far so good, right? Now how do you condense these two guys? R1 0 and R2 1. How do you condense this guy? So if you take the chain rule, see that 1 and 1?
Okay, so it becomes R02.
Right? Can I write this way?
Yep.
So this guy is this guy. The first one is, there is no change in the first one. Then these two guys, this product condensed to this guy here. Then here, this one is, I'm going to apply a little bit trick here. So I multiply by 1. What do I mean by that? So here on this term, see R10 is R10, S is S, and R21 is R21. I added this extra term here. Can I do that?
Yeah.
Because this is 1, right?
Yes.
R is 1. Okay, that's what I did. Now the thing is, so this is again, see if you condense these two guys, then what do you get? These two guys. It's 1 and 1. See chain rule. Then you happen to get R20 here too. You have R20 here. You have R20 here.
So you can factor it out.
Yeah, you can factor it out. So then what are you left with? You have S here in the first term. Then
Yep.
R20 is here. It is already factored out. Then R1S is R1S. Then what are you left with here? R10T, right? That's it. That's the thing.
Yep.
Now let's use this formula here. Do you remember we talked about this earlier? R S RT equals S RA. This is one of the properties we talked about on Monday or last class. So this is called similarity transform. So what I'm doing here is, if you have RS and RT, that can be written as S RA. So how do you rewrite this guy here? This guy, can I rewrite this guy by using this relation?
Yeah.
So what will that be? This will be, so RA. What is your R? R is R10.
Yep.
Then what is your A? A is omega, right?
Yep.
So that's how you get this one. So by definition, again, if you use this guy here, this guy again on the left, what do you have on the left? This guy, right? On the left, if you use this again, what do you get on the left? S R20.
Yep.
This is what you get on the left, and this is what you have on the right. Now, if you equate left and right, then what do you get? If you equate left and right, this is on the left. Okay. So R2 is here, R2 is here, R2 is here, right? R is here. Then on the right, you have this times R2 again.
Yep.
So this R2 and R2 cancel out. See, they're exactly the same thing. R2 0. This guy is R20. On the right, you have R20. They
Yep.
cancel out on the both side. Divide out. Okay, does it make sense so far?
Mm-hmm.
So this guy makes sense. Okay, all right. This guy makes sense. Now, okay, now let's use the linearity of S. Remember we had the linearity of S. Let me show you what I was talking. Yeah, here. Very first one. S A plus B equals AS plus BS, right? So that's called linearity. If you use that, then what do you get here? If you use the linearity, so help me here. So this guy, what do you get? How do you combine this guy using that linearity? Just look at the right hand side only. This right hand side. Can I write right hand side like this using the linearity?
Yep.
So then you have this guy equal to that guy. Now can you compare whatever you have in the argument? Whatever you have, what do you have in the argument here? Omega 02. What do we have in the argument here? Omega 01 plus R1 omega 12.
Yeah.
So can I equate these two? In other words, omega 02, this guy, equal to this plus that. That's what I did here.
Yep.
Okay. So by the way, this guy here, this guy only, the right term, this guy only can be written as this way. It's like this. See that? This 1 and 1 cancel out again. The chain rule. So I'm not going to prove it, but this is what we can do again.
Yep.
So now if you do that, you get simply omega 0, 1, 2. Now what did you get here? Look at this. So angular velocity of frame 2 means nth frame, right? Because just we have 2 links there. Angular velocity of the nth frame with respect to base frame written in terms of base frame is equal to angular velocity of the first frame with respect to 0 frame written in 0 frame. Angular velocity of the second frame with respect to first frame written in 0 frame. So this is all common. Written in 0 frame, written in 0 frame, written in 0 frame is common. That's the beauty. Okay, when you add them together, you can write everything in the same frame. That's cool. Okay, so if you write omega 0, 2, then you have to write omega 0, 1, then 1, 2. It's like, again, the chain rule. See that? 0, 1, then 1, 2, which is 0, 2. This is how we add the angular velocities. Does it make sense so far?
Yes.
So now let's generalize this. So let's make it general. So how do you, so if you, in the general case, what do you do? Suppose you have n link. I'm not going to look at this, all those things. So if you want, you can go over it at home, right? This is everything. So then if you have n numbers of frame, then what do you get? So omega 0 n equals 0, 1, 1, 2, 2, 3, and n minus 1 n, like that. But the beauty is these all are 0. Okay, that's the beauty. So that makes our life too much easy. Yeah, in some cases you will see, that's why I want to alert you to again and again. In some cases you can simply see in the book, some other books, so that guy is written as this guy. So, but don't worry about it. This is just a notation difference. Okay, they're the same thing.
Okay.
So now this is, just to refresh your memory. I don't want to go over it because this is what we did in chapter 2. And here, so remember what we did in chapter 2. Your P0 is D10 plus R10 P1. That's what we did in chapter 2. And we have the homogeneous transformation like this. Okay. So I'll be using this fact here and do something here. Okay, let me show you. Let me finish this, then I'm done. So do you guys have a little bit time? Let me quickly finish this one. Okay, this is easy one. Okay, so what happened is here the frame x1, y1 is moving with respect to x0, y0, and also it is rotating at the same time. X1, y1 is rotating and also moving linearly in this way. Okay, so this q, I have slight change in notation now. This, I call it q now. Okay, so q is rigidly attached. Go ahead.
No, I don't think I ever said anything.
Oh, you didn't see it?
But I just think my microphone glitched. I didn't say anything.
Oh, okay, sorry. Okay, now this q is rigidly attached to frame 1. This is frame 1. Okay, so now we know this guy, right? Homogeneous transformation. We used to call D, but I call it O here. That's fine. So this one was D in the previous notation. Here I'm calling O. So this is exactly the homogeneous representation. Then, and we also know this one. Okay, I'm rewriting this guy. This equals that, right? So P0 equals D10, R10, P1. I'm rewriting this guy like this. So R10, Q Now I have slight change in notation here. Then that D is O.
Okay.
Okay. Now, how do you find the derivative of this P? Help me here. How do you find the derivative of this P here? P dot, right, on the left. Then what is on the right?
R0.
Yeah, this, derivative of first function, then the second function remains as is.
Yep.
Right? So this is what it is. Then the first function remains same as is, then derivative of Q. So you have Q dot here. Do you see this dot here? Okay, there is little dot here, okay? Q dot. Okay. Then the derivative of this guy, O dot.
Just, yeah.
Now remember, as we did before, this Q dot is 0. Remember, we did exactly the same thing before. Q dot is 0.
Yep.
So that's why my second term is 0 now. Now I'm using this equation here. R dot equals SR. So R dot is SR,
Yes.
SR, right? My Q is Q. My Q is Q. And this is obviously 0, and I have this guy here. Now I'm using this rule here. A cross P equals SAP.
So then you can say omega cross R.
Yeah, so this guy, how do you change this guy to? This is left hand side, this is right hand side. Here,
Yep.
here, right here. So which happens to be omega cross R10 Q times plus, this is the derivative of the translation motion. So this is the, now omega, wherever you see the omega part, that's the rotation component. Wherever you see O dot or D dot, that's the translation component. That's why the rate of change of the radius vector, we have two components now, rotation component and also translation component.
Yep.
Okay. All right. So if you want, I can go over this problem. If not.
Do we have anything for homework?
I haven't assigned it yet.
I actually think I still have to do the chapter 2 questions, or chapter 3 questions.
Oh, okay.
But I was going to do those this weekend. I just want to make sure, like, if there's anything else I had to do.
No, maybe I'll assign you guys homework shortly.
I mean, you don't have to.
So do you guys have some time to, I'm being greedy now. So do you guys have some time to go over this? This might be a little interesting to you because, so far we did just derivation and stuff like that. And you'll see number here. So I don't know if you guys feel good. All the derivation only, right? So far we did.
Yeah. I mean, I'm available. I don't have anything to do.
Oh, okay. Then I'll stop it then. All right, guys. Thank you so much.
All right, thank you so much.
All right.
Thank you, sir.
See
Have a good one.
you. Bye-bye.
Have a good weekend. Wow.